Now, a decoder, a basic standard decoder, and we'll go to the lab one day and look at them, play with them. The way we draw a decoder, it's a rectangular shape. You and I, we draw it. It will look something like this. It has n inputs. It will have 2 to the n outputs. It will have a chip enable to turn it on and off, make sure it's on or off. And it will have select. Those are the select. The select is what we have right here, the inputs. So the input, basically, so this would be known as n by 2 to the n decoder. So an example could be like 2 by 4. That's an example of when you have 2 inputs, you have 4 outputs. Could be 3 by what? 8. Could be 4 by 16. Could be 5 by 32. And be honest with you, in the lab, I don't have anything past the 16. So if I need 5 by 32 or 6 by 64, I have to be creative and use more than one decoder to do that. So we'll play with that today. We'll say I need 6 by 64 and you only have 4 by 16. How do you go about making a 6 by 64 decoder when you only have 4 by 16? But before we get to that, let's take a simple one and see what it looks like. Now, the way the decoder works, if you don't see a bubble here, so you have like 2 to the n, let me draw one like a 2 by 4. So let's do a 2 by 4 decoder. I'll make it big and show you what the inside looks like. So this is a 2 by 4 decoder. From the name, it has 2 inputs, A and B, and I don't know which one you want the least significant, which one the most significant. I'll use least significant bit, most significant bit. What does that mean? When I write that, I'll put A on the left, B on the right. So I could have 0, 0 for input. I could have 0, 1, 1, 0, 1, 1. I have 2 inputs, which means gives me 4 selections. I'm going to have 4 outputs here. And if I don't draw a bubble at the end of that, like a little circle, that means only one of these will be high at any given time. So this is, I don't know, what should we call them? Output 0, output 1, output 2, output 3. And here's my chip enable. So for this to work, that means the enable has to be high or low. High. There's no bubble there. If I put a bubble here, for this to work, the enable will have to be what? Low. Some actually work that way with the 0. Some will work with the high. Now, I didn't put any bubbles here. That means only one of these guys will be on at any given time. If this is working, only one of them will be on. Well, which one? If my inputs are 0, 0, this guy is on, the rest of them off. If my input 0, 1, this guy is on, the 1, and the rest of them off. If my inputs are 1 and 0, this one is on, the rest of them off. And if I put 1, 1 only, this one is on, the rest of them off. So then what's going to that? Well, if I drew actually, if I do this inside of that, imagine A, B, and the enable are connected to these. If this is my A, for example, this is my A naught. Okay, I gotta raise it just a hair. I'm looking at it. I'm gonna have a little problem the way I drew it. Let me just raise it higher. This will be A naught. The next one is B and B naught. And the last one is my chip enable. And I made a bubble here. See that little bubble? That means this chip is only going to be working if it's 0, right?
What are you drawing? What are those? Like, what is it? Why do the lines have to go on here?
Because I'm going to attach the gates to them, so I don't have to actually run the wire going. This is the wire going to each one. You'll see in a second there. You know, in the lab you have that board where you can attach 5 volts all the way across. That's really what that is supposed to represent that. So for this to be on, I want it when this is 0, and that's 0. So guess what's attached to it? It's an AND gate. And I do an OR gate. So I'll extend it. That's supposed to be the back end of the AND gate. So I'll go like this. Now that's an AND. And what's attached to it? A naught. That's the A naught. B naught, so that's what these lines, so I don't have to. And E naught. When all 3 of them are 0, 0, 0, 0, this is going to make it 1, 1, 1, and this will be high. This one, it's going to be another AND gate. Ooh, I didn't mean to make it that big. And what's going to that? You want that to be on when it's what? 0, 1, 0. The enable has to be 0 for it to be on. A has to be 0. And B has to be 1. Once you have a 0, 1, 0. This guy is 0 complement, that's a 1. B is 1, that's a 1. Enable 0 complement, that's a 1. This guy will be on. This one will be on when what? As another AND gate. And this is supposed to be on when you have 1, 0, 0. You want the enable for all of them to be 0 for it to work. The enable, because I drew it to be low here. So for that gate to work, the enable must be 0. If it's 0, when you complement it, that's a 1 going to the AND gate, that's good. I want A to be 1, so A is going all the way to the end. And I want B naught. I think that's B naught. Is that B naught? Or
No, that's B.
B? That's B naught. Okay. And the last one, another AND gate. And again, B naught, enable, the naught is going to it. I want A and B going to it. So that's what the inside of that 2x4 decoder will look like. The minute the enable is 1, the minute that enable is 1, what's going to happen to enable not? 0, all these AND gates going to be what? Off. Nothing's going to work. So for this to work, that chip enable, the way I drew them, has to be 0. You make that a 0, and you start playing with A and B. So again, you attach A naught, B naught to this one, A naught, B to attach to this, A, B naught attached to that one, A and B attached to that one with the enable. Go into it. And that's what the inside of that. Only one of these will be on at any given time. Now we have some actually decoders. Only one will be off. They're all going to be on. So that's when they have bubbles at the end. So don't be surprised if you see something that looks like this one. I'll do another one. A 2x4 again, because 2x4 is small enough to show the inside of it. That applies to 3x8, by the way. I'm going to hear a complaint about this, that noise of the pen. I'm getting a lot of complaint about the sound of the pen, like it sounds horrible on the... So here we go. The microphone is right there. So when you drag down, it sounds horrible, I guess. And what you might see now is a knot at the end. Once you see a knot, that means only one of these guys will be low. Not high, will be low. So they're all going to be 1 except one of them will be 0. So output 0, output 1, output 2, output 3. I got again 2 input signals, we call them A and B. And I'll use A as the most significant, B is the least significant. That's because I write them A, B. And my chip enable. So what do you want the enable to be, high or low? Or do without enable. I can do without, you know what? Let me do without enable. Make life easy on me. So if I do without the enable, I can always bring the enable in. If I assume there's no chip enable here, this one. So what will happen? Only one of these guys is going to be low. So again, to show the wires going to it, let me draw A and A naught, and I can attach my gates to them. So if this is A, this is A naught, so it's a wire, and you can just tap to that wire when you want a 0. This is B. And B naught. So instead of AND gate, you want one of them to be low, the rest to be high. So what do? You don't want an AND gate. No, I just gave you a hint. You don't want it to be high, so it can't be an AND. You want it to be the opposite to that. So what do you think? Nope. What's the opposite to AND? NAND. So you're going to use really a NAND gate inside that. NAND gate. And what's attached to this? The knots. I mean, I could have brought the chip enable. I just opted to make my life easy. Notice when they're both zeros, I'm supposed to get what? A 0 here, and the rest of them should be 1. When the A and B are 0, their knot is going to be what? 1 and 1. What's 1 and 1? 1 Complement that, what are you going to have? 0. The rest of them will be a 0. When you complement that, it's going to be what? 1. So all these are NAND gates.
They're all just going to be a 0 output. No, it doesn't matter.
And what's attached to this one, I want A to be 0 and B to be 1 for the next one. Now, I heard the question John was asking, when I put a 0, 0, what's going to happen to this one? Because I said one of these guys will be low, the rest of them will be high. When 0, 0, I'm going to have a 1 here, when I put 0, 0, and I'm going to have a 0, right? What's 1 and 0? 0 complement that, you get a 1. That also will be a 1, that will be a 1, this one will be 0. When I put 0, 1, this will be a 1, the rest of them will be zeros. When you complement that, this will turn to a 0, the rest of them 1s. So this is what? This is 1, 0. So B is 0 and A is 1. And the last one is what? B is 1 and A is 1. That's with the inside. So only one of these will be low, the rest of them will be high. So again, if I'm trying to show you the truth table for it, it will look like this. This is A, this is B, and this is my output. Output 3, output 2, output 1, output 0. The way this particular one we're looking at,
Isn't it just nodding and on?
nodding and AND, yes, that's what an AND gate is. It's an AND with the NOT, right? Is that what you're asking?
Yes.
Yes. So when you have 0, 0, which one of them is going to be off? 0 will be off and the rest of them will be high. When I put 0, 1, 1 will be off, the rest of them will be high. When I put in 1, 0, 2 will be off, the rest of them will be high. And when I put 1, 1, 3 will be off and the rest of them will be high. That's how that gate works, that decoder. Now the other one without the knots is the reverse. When you put 0, 0, this will be high, the rest will be zeros. 0, 1, this is high, the rest 0. 1, 0, this is high, the rest 0. 1, 1, this is high, the rest of them 0. We have them 2 by 4, we have 3 by 8, we have 4 by 16. So how is that going to help me? Okay. Let's take this circuit. Let me just get a graph paper so I don't have to use lines back and forth. I got them here. Let's say we have 3 inputs. So we have 8 combinations. We'll call them A, B, and C. My combination 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. let's make a function. I'll do 3 of them. I'll do 2 of them, actually. Here we go. So these are my inputs, and let's make 2 functions here. What should we call them? F and G? There's F, and there's G. Let's go through F. Tell me if you wanted 0 or 1. The first one.
0.
Next one.
1.
Next one.
1.
Next one.
0.
Next one.
1.
Next one.
1. 1.
Oh, too slow. Next one.
0.
There we go. G. I want it to give me, when it's all zeros, I want to get a 1. I'm just making things up. I want 0, 0, 0, 1, 1, 0, 1. Let's say I want these. And I don't want to go, and let's say I have another one, H. Well, I'm at it. 1, 0, 0, 0, 1, 0, 0, 0. That's it. Instead of doing a K-map for each one, simplifying and see what kind of gates I need to use, I don't have to use any of that. All I need here, 3 by 8 decoder and 3 OR gates. That's it. No simplifying, nothing. So nope, one decoder for all of them. So here's what my decoder will look like. It has 3 by 8. So this is 3 by 8 decoder. That means I have 3 inputs, A, B, and C. And you can see A is the most significant from my pictures on the left from my table here. This is A, B, C. What do you want your enable to be, 0 or 1? 1. Your enable is 1. So what do you do in this case? Attach it to VCC. Leave it on all the time. So and assume A, B, and C are your switches. So you're playing with this switch. As you play with them, you want to see if you get 0 when you put 0, 0, 0. 0 when you put 0, 0, 1. 1 when you put 0, 1, 0, and so forth. I want to see the light go on them. So I attach this to VCC. That means this is always on. So I enable that chip. It's ready to work. So it's based on A, B, and C. I'm going to decide what F, G, and H is going to be. Remember, this has 3 inputs, 8 outputs. Here's my 8 outputs. This is 1. Wonder if I can fit them by skipping 1, 2. 3, 4, there's hope, 5, 6, 7, 8. I have to squeeze. That's output 0, output 1, output 2, output 3, output 4, output 5, output 6, output 7. This, by the way, comes as a chip. It has all the stuff written on it. So now, I said I need just 3 OR function, 3 OR gates. This is for F. This is for G. And this is for H. What are you going to attach to them? When you type in 0, 1, 0, which one of these guys is going to be on?
Just the veins. No, just
O2.
O2, so you want O2 attached here. What else? When you type in 1, 0, 0, which one of these guys is going to be on?
O4.
O4, so you want O4 going to it too. What else we got? 1, 0, 1, which is what?
O5.
O5. So you take O0, O2, O4, O5, run wires to that OR gate. So as you're playing with the switches, once you hit 2, 4, or 5, this gun will be on. The rest of the time, the F will be 0. What about G? When you type 0, 0, 0, you want to be on. So that's what? That's 0.
yeah.
1, 0, 0.
O4.
4, 5, and 7, right? 4, 5, 7. That's what's attached to pin G. I mean to gate G. That OR gate. And what about H? What's attached to it?
0, 4.
0 and 4. So it's one decoder. You could have 20 outputs here, still use one decoder. No simplifying, nothing. Okay. Let's go build it. We go to the lab, and I don't have 3x8 decoders. Damn it, everything is perfect. We're going to build it, but I don't have a 3x8 decoder. I have a 2x4.
Do 2 of them.
Yeah.
2 of them? Okay.
And do something with the neighbor.
Okay. So let me make it a little bit big here. So I'm going to try to make a 3x8. So undo that. We know what a 3x8 looks like. So I am trying to make a 3x8 decoder using 2x4s. So I do want to make a 3x8. So there's my A. This is my B. This is my C. And you said you want to have what? 8 outputs. So this is output 0, output 1, output 2, output 3. Output 4, output 5, output 6, output 7. That's what I want to have. I just put a space between them. So how are we going to make them? You only have 2x4s. No gates, nothing. I don't have any gates. So you want to take a 2x4, put them on top of each other. Here we go. This is a 2x4. And I'll take another one here. So each one of these is a 2x4 decoder. That D, I tried decode, I realized that's not going to fit there. It's okay. This output is going to be attached to that. It has 4 output. That's good. This output is going to be here. This output is going to be here. And this is going to be there. The output of this is going to go right here. The output of this, the output of this, the output of this. Let's assume I put 1, 0, 1. Which one is that you want to be on? What's 1, 0, 1 equal to? 5. You want that to be on. So if I attach C and B to this one, not A, C and B for my inputs. Let me have 2 inputs here.
So it's like a K map.
Not sure what you mean by the K map.
I mean, like one A will be 0, one A for one A will be 1, right?
Well, let's see. If I put C and B going to them, that means I have what? B is 0, C is 1. B is the most significant. I should put B in the bottom, huh? Just to stay with the notation. The one in the bottom, the most significant. The one in the top, the least. Just to stay with that one, because that's what I've been using. So I got 0, 1. Well, 0, 1, it means what? Isn't that 1? That means this pin is going to be on, and this pin is going to be on. 1 and 5. That's a C here. So if I have B and C attached to both of them, that's pin 1, that's 1, and that's 1 for this guy. So both of these to be on, but I want to be that one, not this one. So how would I tell the machine to use this one, not that? Well, I can use the chip enable, attach A to this one. When it's 1, turn this one on, and maybe use a NOT gate, if that's high, because they're identical, to turn that one on. But I said I don't have NOT gates. I don't have OR gates. I only have 2x4 decoders. I can take another 2x4 decoder,
Attach A to each one, right?
now let's see. I need a space. I'll move it closer. There's another 2x4. That's all I have, just 2x4 decoders. Again, it has 4 outputs. Two inputs. This has a chip enable. Let's assume your chip enable is high. Has to be on high to work. So I'll take the chip enable here, and I'll attach that to VCC. That's always on. And you can attach A to either the top or the bottom. It's up to you. Where do you want to attach it to? Bottom? Okay, so you're attaching A to the bottom. You have 2 inputs. You can either attach 0 to this, you can attach 1 to it, or you can attach A to it. It's up to you. There's 3 options. If you attach A to it, When A is 0, you have 0 or 0. Both these guys 0. Which one's going to be on?
None.
This guy, the first one, the 0.
Oh, yeah.
So the way I did it right now, I can take this one, and that could be my chip enable for the first one. This is my chip enable. And when you put 1 for A, you have 1 and 1. Which one is on? The last one. That's your chip enable for the second one. Now, if I decide not to attach A to both of them, I could have put a 0 here. If I attach 0, I'll have what? 0, 0, which is the first, or 1 and 0, which is what? The third. I'll use the third one's chip enable.
Just be different out.
Yep. If I decide to use A and 1 here, A and 1, when that's 0, 1, that's pin 2 for chip enable, 1, 1 will be 4. If I decided to have A here and 0 here, that's 0, 0, which is this guy, 0, 0, 0, 1, which is that one. So it depends on what do you put here. That will determine which one of these to be your chip enable. And now I use 3 2x4 decoders that I have. And by attaching them the way I did right now, I have 3x8 decoder. Only one of these guys will be on. That means one of these outputs will be on at any given time. And again, multiple solution to that. Now, if you're allowed to use NOT gate, then you don't need any of this. You make A go into this, A with the NOT gate go into that one. So when A is 0, complement that, that turns this one on. When A is 1, that turns that one on. If you're allowed to use NOT gate. So when you look at these, it's not just a one solution. We're trying to look and say, okay, what do I have? Like a 2x4 decoders, they come 2 on a chip. I might have an extra one floating there. If I do have an extra one floating on that chip, I didn't use it, might as well use it here. Now again, when you go to look at these chips, which we will go to the lab, the chip will look something. Now this one, we wanted to make out of 2x4, 4x16. So if you wanted to make 4x16, how many of them are you going to need? You need 4 of them. So I'll use all these to enable that chip enable. When it's 0, 0, I'll attach this. So you can't be 0, 1 here. If you need 4x16, you'll have C and D here, and A and B here. And that will make this one, this one, this one, that one on at any given time, or different times. So the design of that for 4x16, it will look something like this. Notice, by the way, the 74-138, that chip, that's a 74, that's one of the chips we have in the lab. It comes with 3 inputs, 3 enables for it to be on. You got to make sure this is low, and that's high, all 3 at the same time. Can you see it? Low, 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 and that's high. A, B, and C, and one of these guys will be low, the rest of them will be high. That's how that chip is numbered. These are the pin configurations. Now, do I have another chip here? I can go in the back of the book and look and see what we have for chip. As we just did decoders here. That's chip enabled, using actually that chip enabled to turn these on. Okay. The next topic, time is it? Oh shoot. I was about to talk about encoders and multiplexers, but we'll do that next time. Encoders, actually, quickly I can talk about them. It's really the reverse of decoder. Just flip the chip, meaning what? Flip the chip quickly. Instead of having n inputs, we'll have 2 to the n inputs and n outputs. Only one of the inputs will be high at any given time, and this will give me the address, almost backward, to decoders. We'll show you where that might be handy, can be used. On your calculator, for example, you can use an encoder that as you press the button. When you press the button, only one of these buttons is actually making contact. When you push down, you're allowing the current to go through it. Only one of these will be high. The rest will be off. Then the next button, you push that one. That one is high, the rest of them off. So we might do that next time, how that encoder works there. And now you generate a code for us. If you push 0, that means 0, 0, 0. If you push 1, 0, 0, 1. If you push 2, make it 0, 1, 0. If you press the 3 and do that, you know. So that's the reverse to a decoder. That's what an encoder is. Then we'll talk about multiplexers. So I'll stop here.